Let's look at some details of the core. Again, this is a basic introductory course, so we are not going to go too much into the details, but here is a lovely infrared image from satellite. I think this was Hurricane Irma, September 12, 2017, and I like it because you can literally see the ground from up here, and that kind of a strong eye, very clearly defined, implies very strong hurricane with a strong eye wall, and you can see the darker images in the interior getting lighter as you go out, and you can obviously see the spiral bands as well as the structure that we are looking for. So the core forms once the initial tropical disturbance forms into a tropical storm. The incipient storms has a strong convection, deep convection that is needed, and the circulation convergence at the lower levels feeding the deep convection and divergence at the top, and you have these rain bands already kind of formed, but you can see that in the center the eye has not formed yet. But once the intensification starts, you have such a strong tilting eye wall that the convection here begins to produce a downdraft in the middle, which is going to create this subsidence, drying, and minimum winds, warming, compression and warming, and create the eye wall, create the eye with the lowest pressure. Then you have very strong pressure gradients here, very tight circulation, and as we talked about before, the inertial stability and the intensification and so on all depend on how strong this vortex tube is. Here is another visible image of the eye and the eye wall of a mature tropical cyclone. So eye wall here slopes outward from the surface, as we see here. It's what's called a stadium effect here, and you can see the ocean to the bottom when the eye wall is very clearly defined, and a lot of the aircrafts fly over it to watch inside what's happening. And here is a schematic of how this circulation works. So the cross section through a tropical cyclone shows the vertical airflow, which is, as we saw before, very strong in the eye wall, where you have the strong winds and heaviest rain, and you have subsidence in the eye itself, and we have these cirrus once the convection reaches the top, hits the ceiling, and then begins to diverge out, producing these cirrus, whereas the subsequent rain bands also have vertical motion and sinking subsidence between each of the successive rain bands, as we saw before again, but these vertical motions and the rain amounts are smaller than in the eye wall. So obviously the winds begin to drop off, the balance begins to change from cyclostrophic to gradient wind to maybe even geostrophic as we go outside, and you can also see that the faster rising air can produce ice crystals, snow and graupel, as well as raindrops, whereas here you have not as much of a fast rising air, and the expansion and cooling will be lighter, and so on and so forth. Also all those details happen. The more recent cyclone behaviors have involved what is called rapid amplification. The definition is an increase in the maximum sustained winds, 1 minute average or 10-minute average, depending on where you are, but that within 24 hours they have to intensify by I think 55 meters per second or something like 15 kilometers per hour, I think, and then 30 knots, so you can look that up. Here is another beautiful image of a very well formed eye wall, showing very nice structure going out. Rapid intensification is being studied. It's not completely understood yet, but there are many good empirical information data that's available that has some specific features, and just like the rest of the cyclone formation in the model, cyclone forecasts, the understanding is going to advance, or the modeling is going to get ahead of the process understanding. And this ensemble simulation study by Shun Lee is showing early rapid intensification onset in the ensemble member and a late rapid intensification onset member. Remember, ensembles have several members generated with some technique of perturbing the initial conditions and so on and so forth, which we will not get into. But when there is early rapid onset member, you can see that the vertex is standing up straight, it's strong, its inertial stability is very high, so it's not easily affected by perturbations, whereas in the late RI onset member, the vortex is tilted and it doesn't have as solid as a strong structure as here, and you have low circulation creating convergence on this side, and there is the shear, and there is updrafts that are feeding the down shear side here, and you can see this convection has gotten much stronger compared to here, whereas when in this case there is also this updraft going towards there. The lower circulation is weaker, the convergence and the updrafts are also weaker, the whole structure is weaker, and you don't have as much of a tall deep convection. There are details like convective bursts in the eye wall, how much it has to warm in the eye, and how that rapid warming feeds the energy to the rapid intensification and so on. But I just wanted to include it as part of the details of the core, because the core does play a key role now in terms of the processes that are leading to more and more rapid intensification, which is happening also in the Indian Ocean cyclones recently. In fact, the last one, Tauktae, in May 2021 rapidly intensified in just 2 days, whereas the others before had intensified in 4 to 5 days. So this has to be watched very carefully, especially combined with the other features of the cyclones, that they are moving slower, they are stalling near the coasts, dumping more rain, of course rapidly intensifying, and more of the cyclones are reaching the stronger categories. Total number of cyclones may not be increasing, but more are becoming the strongest category cyclones. So we will at the end look at a brief summary of what we know about the impact of warming on the cyclones overall, but for now we will leave this at this brief introduction. Okay.